Hello, this is Dr. Mohammed, and this is another video under Design of Steel Structures according to AISC course. And today I'm going to talk about the compression members, part 1. We're going to have different parts, and the brief contents of today's video is going to be an introduction in the beginning. After that, I'm going to talk about the column theory, which is having something related to the critical buckling stress and the effective length after that. And I'm going to talk about the AISC requirements for LRFD and ASD for the design or for the compression member critical buckling strength. And then I'm going to talk about local stability. Okay, now let's go to the compression members introduction. Whenever we think about the compression members in general, we need to think about them as structural elements that are subjected only to axial compressive forces. That's an important issue, that compression members here means that pure axial compressive forces, because we are going to deal with other type of element which is going to be titled with beam column elements, where that we are going to find the element is receiving some compression forces or compressive forces, and in addition there is flexural or moments that is going to, or moments or flexural straining actions going to develop due to moments that is going to be resisted by this beam column. So here we are talking about compression members, and it is only related to or subjected only to axial compressive forces. That is, the loads are applied along the longitudinal axis through the centroid of the member cross-section. This is an important issue regarding our element. The stress can be taken as P over A, means that the force that we are having, the compressive force over the area of the cross-section, where F is considered to be uniform over the entire cross-section. So whenever that we are having the cross-section here, we are considering that the whole cross-section is going to be uniformly distributed with the compressive stress. Okay, so it is going to be, the compressive stress is going to be uniform here. This ideal state is never achieved. To be realistic, we are not going to achieve it. We need to be realistic regarding this issue in reality. However, because some eccentricity of the load, is inevitable. This means that we are, in reality, we cannot avoid small eccentricities that is going to make this assumption to be almost impossible. Okay. Bending will result, in this case, as long as there is some eccentricity, there would be some bending that we are expecting to take place. But it can usually be regarded as secondary and can be neglected. That's very important. So the point is, there are some extra, or there is additional moment, but we are going to consider it as secondary and can be neglected. Okay, if the theoretical loading condition is closely approximated. Commonly we are following this. So whenever we design compression members in general, we are assuming that the load is concentric. However, that reality, as we said, reality says to us, no, we are going to have some eccentricity of load. Okay, it is something inevitable. And if there are some additional moment coming from this eccentricity, we are going to neglect it. We are going to say that they are not going to contribute, or they are not going to be the primarily main straining actions controlling the behavior of the element. Bending cannot be neglected if there is a computed bending moment. That's very important. Computed means what? If we have like column and we have beams here, and we have some moment on the beam, then definitely that we are going to have computed moment on the column. In this case, this vertical element, we call it something else. We do not call it column only. We call it beam column. So we consider situations of this type in chapter 6 of the textbook, which under what we call it beam column. Okay. Now let's go to the compression members types. We have different types of compression members. You can find these columns in all of the buildings that you can see, gravity columns of steel and composite buildings. You can find them in bracing members. You are going to find in the bracing here, the red ones here, okay, and even this vertical also column. Okay, you are going to find it in diagonal members and elevated tanks. You are going to find this is purely going to take this load, lateral load, by resisting it through compression. Okay, and you are going to find it compression members and truss structures. As you can see here, these red elements, they are going to be under compression, and the top chord as well. Arches, of course, it is under compression. Okay, similar compression members not classified as columns are referred to as struts. Sometimes we cannot, for small elements, we tell that the element is working as a strut, smaller. So we're talking about smaller compression members, not classified as columns, are referred to as struts, as you can see here. Okay, if we have like house roof, there's a weight here, and these two elements considered to be struts. And the horizontal one is going to be like a tie, where that it is going to be the floor beam. This is like tensile or tension member. These are compression members. Similar here, if we have a canopy, for example, this is the beam here. This is commonly, it is strut. It is going to receive compression force. However, this is the tie that is going to receive the tension force. Okay. Another thing which is related to compression members, generally are going to find it in trusses, or going to find, as we said, this member, for example, here, it is considered to be under compression, under this loading condition. Trusses in general, if we have loading here, we are expecting that this member to be like under compression. Similarly, we are going to find, as we have said in the previous slide here, if we have loading here, we are going to have some elements to be like under compression, as you can see. And also, I've mentioned about the towers, of the towers in cable supported bridges. We are considering them as compression members. Okay. Okay. Now we are going to talk about compression terminology. Compression terminology. We are going to commonly we're going to use them throughout our lectures, so it's better for you to familiarize yourself with them. First of all, we are going to mention about something like the moment of inertia. Okay, and the moment of inertia equals to, I think that you know well about this, but again, it's like a reminder of what you have studied before. The integration for what we call it the area times the distance of this area to the centroid or to the neutral axis squared. So this is the moment of inertia. Okay, we call it the second moment of inertia. Parallel axis theorem, whenever that we are having like a neutral axis and we have some area here, so we are going to take the moment of inertia around the this axis, and then we are going to use the parallel axis theorem in order to calculate the moment of inertia around this axis of the whole composite section, for example, if we're talking about it. Okay, so in this case we are going to have like Ix, which is the moment of inertia of the element around its local neutral axis or horizontal axis here, and then we are going to use area times x squared, where that x is going to be this distance between the neutral axis, local neutral axis, and the global neutral axis. And then we are going to talk about radius of gyration, which is, we denote it with small r, the square root of I over a, which is the inertia over the area of the cross section. Effective length is going to be KL. It is not the length, effective length. So effective length means that we have, this is the original L if we are having an element like this, for example. Okay, so commonly L is the distance between here to here, whereas the end ends of the element. But whenever that we're talking about effective, maybe the effective length is going to be something smaller than this, which is the length that is going to buckle exactly. That is here starting from the inflection point. So the length is the distance between the ends of the column or the element. However, the effective length is the distance between the inflection point, if we're talking about moment, for example, or the point where that the axis of the element is going to start to bend or change. So we can consider it as the inflection point and start to measure the length based on these new points. K is a factor that is going to be used for this, for calculating or giving the effective length. Slenderness ratio, which is going to be KL but over R, which is over the radius of gyration that we have explained here. This is commonly are going to be used commonly actually through our compression member equations. Principal axes, major and minor. So whenever that we are looking, for example, for an angle, we are going to find that we have the major and the minor axes, okay, that is going to give us the maximum and minimum, or the two that is going to be considered the major and minor principal axes of this element. Okay, critical loading, P critical, which is, we're going to talk about it in detail. Okay, the loading that is going to trigger buckling, okay, in the element. Factored compressive strength, we call it factored compressive strength, we call it CR. We are going to see all of these terminologies and annotations later. Okay. Now let's go to the column theory and try to understand more about it. Okay. First of all, whenever that you are going to put the same loading, okay, the same compressive loading in two different types of columns. One is so thin and the other one is stocky, okay, it's thicker than the first one. You are going to find, this is something that you can find and you can see by your eyes, that whenever we apply the same loading, you are expecting this thin or slender column to buckle. So the dotted line is the buckling of this thin or this slender column. And if you increase this loading, we are expecting that this column is going to fail by buckling. However, whenever that you put the same loading on a stocky column, means that thicker column, if you are going to increase this P, you're going to find that it will fail by compressive yielding rather than buckling. Means that yielding means that the material itself would yield, okay, at certain location, okay. It's not going to buckle as this one. So the failure mechanism of slender column is different than the failure mechanism of the stocky column. We say that this slender column is going to fail due to buckling, exactly. However, the stocky column, it is going to fail by compressive yielding rather than buckling. So there is compressive yielding here, that is at any section it is going to yield first, and then the material is not going to withstand the loads applied on it. So this is the first understanding that we want to understand, that there is a relation, okay, or there is something that we want to notice, which is, as you can see here, some long column and thin and short column and thick. We call this slender column, we call this stocky column. And we realize that the failure mode of slender columns, it is going to be by buckling. However, for stocky column, commonly it is going to be by compressive yielding. Okay. Now we want to know what is the limit that we can use for this. What is the limit for the loading that we are talking about? We here just like Sarah mentioned, there is loading, which is P, but we do not know what is the loading condition that is going to make this buckling, for example, take place. So we found that there is something that we need to understand, which is if we have like pin, end conditions for our element, we are, and with this element L, the length is L, and we apply loading on this element, okay, we found that there is something called, there is a level of loading called PCR, which is the critical loading or the critical load. Okay, we sometimes refer to it as Euler load or Euler buckling. So what is this PCR? You're going to find at this level of loading, we are going to find that our cylinder column or this column is going to buckle. And if we increase the loading more than this PCR, we are going to find that buckling failure would take place here. And we found that sometimes it's based on in the column itself that this PCR is going to trigger different modes of buckling. We call it buckling modes. Sometimes it is going to be a single wave like this, or something like S, something like this, or like another buckling mode, as you can see. Okay, and we found that this PCR, okay, due to Euler investigation, we found that PCR, or the critical buckling load, is a function of, as you can see here from this equation, it has something or relation with EI, the inertia of the cross section itself, and it has something to do with the L, which is the length of the column. Do you remember when I was talking about this? Talking about the cylinder column? This is thin and long. This is thick and short. So now these, the characteristics that we were explaining here, actually it has been interpreted to equation here. So we have pi squared EI, which is representing this, the inertia, and there is L, which is representing the geometry of the element itself, which is L. Okay, and we found that at the end we can put it in this form if we are going to say that I, as we have explained in the previous slide, okay, it has something to do with the radius of gyration, and with r squared times a, it gives us I, and then this r squared is going to be in the denominator of the denominator, and it's going to be L over r squared, L over r, said that it is the a common term that is going to be used frequently. Okay, now I want you to look to this, okay, I want you to look to this equation, okay. So first of all, we need to notice something. In this equation, there is what? There is no mention about the yield of the material. So I didn't mention here F yield, right? And I didn't mention also F ultimate. What does it mean? Means that if we are having a member with different types, okay, with different types of steel grade, okay, then we are not, it is, the PCR is not going to be function in this, okay, I mean in this F yield or F ultimate or the grade of the steel. It is only function of EI, okay, and L. Remember that E, it is what? It is Young's modulus, stress-strain slope, or the slope of the stress-strain curve for the steel, which is going to be constant for all of the type of steel, right? So all types of steel, they are having this constant E. So that's very important, and keep it in your mind. The critical buckling is having it has something to do with the EI, the inertia, and the length. It has nothing to do up till now with F yield or F ultimate of the material itself. Okay, keep it in your mind, and I'm going to recall it later. Now, collapse by buckling is going, it's like a global phenomenon that can take place for weather that we are talking about. Steel, look here for this, for example, it's a steel column, and then we are applying the load, compressive load, and we found that this is the buckled or the buckling shape here. It failed here, buckling failure. This is steel cross-sectional area or steel element, If we're going to talk about concrete or RC concrete, as you can see here, this is the buckling here. This is real buckling failure. Here another very clear buckling failure that you can see here. This is for compression members. Okay, so the point is that we have a critical buckling load or Euler load, and if our load is increasing or like going beyond this PCR, which is the critical buckling load, then we are going, or we need to expect this buckling failure mode. Okay, now let's have an example regarding this issue. So if we have a wide flange 12 by 50 cross section is used as a column to support an axial compressive load of 145 kips. So we have like wide flange and the load that is being applied on this element. Okay, we're talking about like pin here. Okay, and the load that is being applied, as we said, it is 145. Okay, from both sides. The length is 20 feet, so we are talking about a length here which is 20 feet, and the ends are pinned, as you can see here. Without regard to load or resistance factors, investigate this member for stability. Okay, so now I didn't mention here at all anything related to F yield. What is the grade of the steel? We didn't mention, right? Why? What is the reason? Because the grade of steel need not be known. The critical buckling load is a function of the modulus of elasticity, not the yield stress or ultimate tensile strength. Okay, so that's the point here. Just we know this cross section, we can obtain EI for it, right? Knowing it, and then we can go and see this L, then we can obtain this PCR. So for wide flange 12 by 50, minimum R is going to be RY. Please stop the video here and go to the manual, your manual, and then check what is the minimum radius of gyration for a wide flange 12 by 50. We're going to find it RY, and it equals to, the radius of gyration is 1.96 inches. Then this means that the maximum L over R, the slenderness ratio L over R, is going to be 20, which is in foot, times 12. This is convergent to inches, and then over R, 1.96 gives us 122.4. Okay, so now we obtain this L over R. Why we need it? Because we need it to put it in our critical buckling load or Euler load. Pi squared PCR equal to pi squared EA. Okay, EA over L over R squared. Okay, so this means that we are going to put in the denominator 122.4 and in the numerator 29,000. This is constant for all types of steel. No need to know what is the type of or the grade of steel. It's constant. Okay, and then the area, it is 14.6. We're talking about this wide flange. So please stop the video and check this value from the manual. Then you're going to find this PCR. The critical buckling load is 278.9. However, that the applied one is 145. This means what? We are in a safe side. Our section critical buckling load is almost 280. However, that the applied load is 145. It's far less than our critical loading. So our section is what? Is okay. The section is okay for being a compressive member. Because the applied load is 145 kips is less than the PCR, the column remains stable. So there is no instability issues here, and has an overall factor of safety against buckling equal to this loading over 145, which is the actual loading, and it gives us almost 1.92, almost 2. So it is, we are on the safe side. Okay, now this is a very simple and straightforward example on this equation that we were talking about. Okay, this equation that we are talking about. Okay, So now we realize that we have something to do with EA and L and R, but there is nothing related to the F ultimate or F yield. Okay. Okay. And we are going to find that according to this stage only, what we have to know is, like as I said, E, I, or A, for example, and the radius of gyration. That's it. Okay, radius of gyration. Okay, now let's go to the next, which is talking more about the critical buckling stress. The critical buckling stress. Okay, critical buckling stress, if we are going to understand it, we need to understand a behavior, okay, a relation between something, we call it FCR, okay, the critical buckling stress, and L over R, which is the slenderness ratio that we have explained before. For any material, any type of material, whether that is steel, wood, rubber, whatever, the critical buckling stress can be plotted as a function of slenderness. We call this the horizontal axis to be slenderness, as shown. We found something that is very interesting here. If you look deeper into this graph, you're going to find something very interesting. First of all, you're going to find that a horizontal limit here on this graph that the graph does not exceed, which is F yield. Remember that the vertical axis is stress, okay, FCR stress, or we can say that it is buckling stress, okay, or the stresses on the material itself. So found that F yield is considered to be like the upper cap here, limit, upper limit. And you're going to find that there is a point here on the graph where that the graph is seemingly to be changing from one pattern of curvature to another one. Okay, there is a point here, and this point considered also to be a limit on the horizontal axis. So we have a limit in the vertical axis, and we have another limit on the horizontal axis. Okay, okay, and we are going to find something that is very interesting here. If we are going to plot another relation between F, the stress and the strain, for any material, for the steel, for example, we're going to find something common like this. We understand it or we are familiar with this. There is a relation between stress and strain, as we can plot it here, as we can see it here, and it's plotted in this way, that this part is elastic and there is a transition part here. Okay, let's assume that here from this point we are finding a transition part until that we reach here, and then it's going to be constant after that, right? So this constant value on the vertical axis, it is F yield. And the start of the transition is going to be point here. We can say that this point called F proportional limit, PL, F proportional limit. Actually, whenever that we start our material, we start on loading our cross section of this material, we are going to find that the stress strain curve is linear in this part. Means that E, which is the slope of this part, is constant. So when the loading is being increased and the stress is being increased until we reach to a certain point called FPL, E is constant. We found that buckling can be described by an equation. Okay, and this equation is going to take into consideration E, as we have explained before. So our FCR in this case is going to be, which is the buckling or the critical buckling stress, is going to be pi squared E. Take care of this. E is what? It is the slope of the linear part, okay, over L over R to the power 2. But we found that whenever the load is increased and the stress is exceeding this FPL, which is the proportional limit, we found that this part, until reaching F yield, E is going to be changing. So we need to find that E is what? Decreasing. And this is going to be denoted with another type of E called ET, which is tangential. Okay, and as you can see here, this tangential Young's modulus, or the slope, is much less than the original elastic one. And we found that when we increase this to the limit, we found that the critical buckling stress is going to be changed. Okay, it is not going to be this anymore, but we found this part is going to be like the governing graph. And we are going to find that the same equation is going to be used here with one major difference, which is exactly ET is going to be used. ET is going to be used in this case. Okay, so this is the relation between the stress strain curve and the critical buckling stress versus the slenderness ratio. Okay, now we found that this proportional limit, which is horizontally, is related to the FPL, the proportional critical buckling stress on the critical buckling stress vertical axis. And the horizontal one, we found this critical, we can say this is also like a point that is on the horizontal axis, on the slenderness, that is going to differentiate between two different behaviors of the compressive element or the compression element. The lift part is going to be denoted with inelastic buckling, and the right part is going to be elastic buckling. In this part, the column is going to elastically buckle. However, in this part, the part of the column, part of the cross section is going to yield, and the remaining part is going to buckle until we reach to some point where that the entire cross section is going to yield and there is no buckling at all for any part of this section, which is going to be here. Okay, and this is the this point slenderness ratio means what? Exactly, it is stocky column. So we're going to find that yielding is going to take place here. However, that if we go along this horizontal axis until this limit, for example here, we're going to find what? Slender column is going to be there. Buckling, elastic buckling will take place, no yielding here. So where is the limit between the stocky here and the slender column? We can say this is the limit between the two. Okay, I hope that you understand and you are making like a kind of relation or a link between the two, stress strain curve and the critical buckling stress versus the slenderness ratio curve. Okay. Okay. Now we can read this. It's a very nice comment on the book. I'd like to read it with you so that we can get more understanding of it. Early researchers soon found that Euler's equation did not give reliable results for stocky, like here. So the researchers found that Euler's load is not giving accurate results for stocky column, okay, or less slender compression members. So they found that there is something wrong with Euler's equation. The reason is that the small slenderness ratio means that we are like here. This is the slenderness ratio. This is high slenderness ratio. Here is very low slenderness ratio. Okay. So they found that the reason is that the small slenderness ratio for members of this type cause a large buckling stress. Okay, and this is right actually here, because the small slender, actually the buckling stress is going to be, as we said here, it is going to be large. Okay, if the stress at which buckling occurs is greater than the proportional limit of the material, the relation between stress and strain is not linear, and this is right. If we go back here, at this point, which is at this point here, we found that after that, if the stress is going to be increased, the relation is not going to be as we have. This is actually Euler loading, Euler buckling equation. We found that at certain limit, Euler buckling equation does not work. We found that, look here, this is the dashed line. This is how Euler loading is going to give us. So it is not going to give us accurate values. The accurate values are the solid lines here. So this is the Euler loads, but they found that at certain limit, which is FPL, we call it the proportional limit, Euler loading is not going to give us accurate results. So why? Because here he is working only on E, But actually on this transition part, E is going to be changing because ET should be used. This part is going to use ET. Okay. The relation between the stress and strain is not linear, as we said, and the modulus of elasticity E can no longer be used. Okay. Remember in the previous example, if you remember, we have like our loading was 200, critical loading was 278 from the previous example over the area, which is 19.1, right? So the stress at buckling was 19.1 ksi, which is well below the proportional limit for any grade of structural steel. This means that our example that we have here, this is the example that we were talking about. This example, the critical loading, this is in kips. If we say that the stresses, it is well behind, it is really in the slenderness part. Okay, it is. I mean that it is going to be a slender column. Okay, this is why they said that, which is well below the proportional limit for any grade of structural steel. If we're going to look to the proportional limit, then our element, our example, it was something here, for example, or here. Okay, so it is far less than even the proportional limit. Okay, okay. Okay, so now this is the point. This difficulty was initially developed this difficulty was initially resolved by Friedrich Engelsherr, I hope that I read it right, who proposed in 1889 the use of variable tangent modulus FT. Okay, and this is in equation 4.3. You can find it in the book, which is already I have mentioned, which is the buckling stress equation for a material with stress strain curve like the one shown in the figure 4.5. Let's go back here. This is the figure 4.5, and this is the stress strain curve that we are having here. Okay. Okay, E is not constant for stresses greater than the proportional limit, as I have mentioned. The tangent modulus ET is defined as the slope of the tangent to the stress strain curve for values of F between FPL and Fy. If the compressive stress at buckling PCR over A is in this region, it can be shown that this equation is going to work for us. PCR equal to pi squared E T here, L over L. Okay, now let's go to note that ET is smaller than E, okay, and for the same L over R corresponds to a smaller critical load PCR. Because of the variability of ET, computation of PCR in the inelastic range by the use of this equation 4.5 is difficult, which is the one that we were talking about. This is 4.5, which is ET. ET, it is difficult to calculate the tangential Young's modulus. Okay? Okay. In general, a trial and error approach must be used, and a compressive stress strain curve such as the shown in this figure, which is figure 4.5, must be used to determine ET. So we are going to determine this ET from here to here. At each point, can you imagine that each point that we want to calculate ET corresponding to each stress, which is something difficult, okay? For this reason, most design specification, including AISC specification, contain empirical formulas. So this is why, this is the main reason that you are going to see in the next slides, empirical formulas. Why? Because we cannot use, or we cannot calculate it accurately. It's a little bit difficult, and it needs a trial and error approach, okay, especially for inelastic columns. We are talking about inelastic part here, starting from here. Okay, okay, that's very nice. Now let's go to the effective length, and let's study more about it and understand it more. Okay, the effective length, as I've mentioned before, that is going to be L here, which is, sorry for this. So the effective length is going to be, as you can see here, between the inflection point, for example, if we have a fixed hinged end conditions for this column, and this is L. In this case, we are going to find this is the buckling wave length. This is what we call it, the effective length. Okay, and we need to know that both the Euler and tangent modulus equations are based on the following assumptions. So we have like two loading or two Euler loads now, if we want to say, one related to or using E, the other one is using ET, the tangential one. So there are like three main assumptions that we need to put in our mind. The first one is the column is perfectly straight with no initial crookedness, okay, which is something in reality it's extremely difficult, but anyway, this is the first assumption that we need to go, okay. And the second is the load is axial with no eccentricity at all. Also, it's very difficult in reality, but we need to take these two assumptions seriously. Why they are putting these assumptions? Because of this. Because we need to say that there is no bending moment in the member before buckling. That's very important. So these two assumptions are being given for this reason, that there is no bending moment. We are applying only if we're applying pure force, for example. So we are not going to say that there is any kind of bending moment here. Okay. And then the column is pinned at both ends. We need to be, whenever that we use this buckling, Euler buckling loading, we need always to think about that pin connection. Okay. Other type of connections, he didn't study it, and we are going to study it in detail. But anyway, this is only for the case of pin-pin connection. Okay. KL is the effective length, and K, we call it the effective length factor. Okay, so whenever that we see this K here and K here, this is what we call it the effective length factor, that based on which we can calculate the effective length. The use of the effective length KL in place of the actual length L in no way alters any of the relationship discussed so far. So do not worry that we are using here KL or L. It does not have any kind of impact on the equation, because before, if you remember, we were talking about L here, right? Every time we were talking about L here. But now, all of a sudden, we put KL. It is no problem at all. It has no effect at all. So on this graph, for example, the column strength curve shown in this figure, which is figure 4.6, is unchanged except for renaming the abscissa to be KL over 4. So instead of looking to this curve as the horizontal line is L over R, we are going to put K only, KL over R. So that's going to be our case here. Okay. And the critical buckling stress corresponding to a given length, actual or effective, remains the same. So no problem at all. If we change this, instead of L over R to be KL over R, the corresponding critical buckling strength will not change. No problem. Whatever that being said here, what we want to end up is this graph is going to be the same if we put only small k here. This is what we want to say at the end. So nothing is going to be changed if we put k here. Okay? Okay. Now let's go. I already mentioned about that these three assumptions, why we need all of them. So the first two, it is needing the first two conditions mean that there is no bending moment in the member before buckling. And the last one, the column pinned at both ends, the pinned end condition requires that the member be restrained from lateral translation but not rotation at the end. So their concern is like lateral translation here. Okay. Constructing a frictionless pin connection is virtually impossible. So even this support condition can only be closely approximated at best. Okay, all of them actually they are difficult to be achieved, but we need to work on this, on these assumptions and use them in the derivation of our equation. Okay, now let's go to the AISC requirements for compression members. First of all, we have LRFD and then we have ASD. Let's start with the LRFD. The basic requirements for compression members are covered in Chapter E of the AIC specification. The nominal compressive strength, we call it nominal compressive strength. You're going to find it in ASIC equation E3-1, and this means that, or it is written like this, Pn, the nominal strength, okay, nominal compressive strength, equals to FCR times area gross, okay, where this Pn is the nominal compressive strength. And for LRFD, we are going to reduce this Pn by multiplying it in by resistance factor for compression. Okay, commonly we use it 0.9. So our P ultimate, which is the sum of the factored loads, should always be less than or equal to the resistance factor for compression, which is 0.9 times the nominal compressive strength. These two together, okay, we call this the design, we call this the design compressive strength, and as I said, that phi c, or the resistance, is going to be 0.9 according to AISC. Okay, so remember this, we use the word design compressive strength. Okay, and for ASD, you're going to find that PA, which is the sum of the service loads or the actual loads, should always be less than or equal to Pn over safety factor. Pn, it is going to be the same as the nominal compressive strength. It has nothing to do whether that we are using LRFD or ASD. Okay, so it is similar as here. Okay, it is similar. So for ASD or LRFD, they are going to be the same. So this is the condition that we need to achieve. Where P, it is the sum of the service loads, Pn, nominal compressive strength, omega C, it is the safety factor for compression, which is taken 1.67 according to AISC. And this ratio, which is Pn over omega, it is going to be called allowable compressive strength. Okay, now if we are going to use stresses formulation rather than forces, then we are going to use this formula, which is FA. Just we are using like FA should be less than or equal to F another A. Take care that this is lowercase here and this is uppercase. So the smaller lowercase here, it is F, means that computed axial compressive stresses, and the capital one or uppercase, it is allowable. So the first one, this is computed, this one is allowable axial compressive stress, and then we are going to use our famous equation here, which is FCR over omega C equals to FCR over 1.67. As we said, it is given 1.67. Then it equals to 0.6 FCR at the end. This is the limit that we should use. Okay, now let's go to the Euler loading and Euler stress, and to finalize this, the loading or the FCR that we are searching for, because here we are putting FCR, right? So this means that we need to know what is FCR and how we can obtain it. Okay, how we can obtain the critical buckling stress. Okay, so Euler loading, or we call it Euler load or Euler stress, both are okay. So it equals to, this is, we call it PE, means that Euler PE, pi squared EA over KL over R squared. We know every element here, and if we are going to use stress instead of loading, then means that we are going to divide by A, then A is going to vanish from here. Okay, we put A here, so A is going to vanish, and then we are going to end with pi squared E over KL over R. Okay, this is how we are going to use. We found that with a slight modification, this expression will be used for critical stress in the elastic range. So if you remember that we have like something like this. So we have like one part like this, another part like this. sorry, I'm going to make it better. So if we have something like we have here and then we have here, something like this. This is the point where that we have the proportional limit. So the point is we are going to say that for the part of the elastic range starting from here to here, this is the elastic range of buckling. Then we're going to use this FE, okay? We're going to use this FE, but we are going to decrease it a little bit. Why? Because we are considering that there is what? Initial crookedness. Do you remember that? In our assumptions, we said that. If we go back to our assumptions, remember? That is no initial crookedness. Well, we are putting it as an assumption, but as I said that in reality, this would not be. It is something inevitable. We cannot avoid. So this means that we need to be realistic also in our equations. So instead of using FE only, we used like a kind of reduced FE. So it is FE the same, but instead of using here 1, it is reduced. This one is reduced by like almost like 13%. So we multiply by 0.877. So if I'm going to ask you, what is the reason for this factor, 0.877, you're going to tell me this is due to what? Yes, to take into consideration or to take into account the effects of initial crookedness. So to obtain the critical stress for elastic columns, the Euler stress is reduced as follows. Okay? To account for the effect of initial crookedness. For inelastic range, if we go back here, for the inelastic range, right here, this is the inelastic range, we are in the range that we need empirical formula. So this empirical formula is going to be given for us, as you can see, FCR, okay, it is going to be 0.685 to the power F yield over Fe times F yield. Okay, so from where we can get this, it is, as we said, it is based on empirical formula. Okay, ASIC studies could suggest it for us. For inelastic column, the tangent modulus equation, which is equation B, 4.6b, is replaced by the exponential equation. Okay, so let's go here. We have like A and B. Yes, remember here we have A and B. So the A, it is the effective one for the elastic. This one using AT, it is for inelastic buckling. So this ET, as I said, E, it is very difficult to be calculated and we need a trial and error process and so on and so forth. This means that we need to put empirical equations. So the ASIC is taking advantage, or at least he overcame this problem by replacing this equation, which is the ET, where that E was AT, okay? It has been replaced with this empirical equation, which is going to be easy for us to use. Okay, now let's go to the summary of what we have said for compression member. Now we want to put a limit for us. First of all, for the horizontal limit, for the horizontal limit, which is KL over R, and the vertical limit FCR. So for the horizontal limit, we're going to put this limit here, which is 4.71 times the square root of E over F yield. This is the KL over R limit, the slenderness ratio limit. Okay, so we're going to put it as for KL over R smaller than the limit, or KL over R larger than the limit. So first here, smaller than or equal to the limit, here larger than the limit. Then what is the equation, the governing equation? This part, it is what we call it inelastic buckling. However, here we put the elastic buckling. Okay, remember that very well. You are going to find this equation in ASIC. Okay, the complete specification is going to be given like this, that the limit is given here, KL over R less than or equal to the 4.71 times the radical, or F yield over Fe should be less than or equal to 2.25. So we are having here or. We need to calculate this term or this one. Okay? And FCR is going to be, this is, as we said, for inelastic buckling, and you can find it in equation E3-2 in ASIC. And for the other case for elasting, we are also going to take two types of limitation. The first one is the slenderness ratio limit, and the second one is going to be related to F yield over FE. Okay, so F yield over FE, and we need to calculate both of them, and after that we can use FCR equal to this value, which is 0.877 FE. You can find it in equation E3-3 in ASIC. Okay. The mode of failure considered so far is referred to as flexural buckling. Yes, that's an important note that I want to. Whenever that we are going to use this curve, what will happen for the structure, or what will happen for our column, that it is going to buckle, right? We call this flexural buckling, as the member is subjected to flexure or bending. Okay? When it becomes unstable, because whenever that the member is going to be under the axial force, as I said, buckling mode failure is going to take place. So as if this buckling failure, it is as if the member is subjected to flexure or bending when it becomes unstable. For some cross-sectional configurations, the member will fail by twisting. We call it torsional buckling. It will not go only in this direction or in this plane. It is going to be maybe in a plane that is having an angle with the plane of this whiteboard. Okay? Or by a combination of twisting and bending. We call it flexural torsional buckling. Okay? We're going to consider these types of failure later on in our videos and our lectures, but now what we are describing up till now is related to what we call it flexural buckling in one plane, as I have shown to you in the pictures that you have seen here. Look here, this is what we call it in one plane only happen, or this kind of failure took place. Okay, one plane, something like this. But sometimes the structure is going to, if we are going to say, it is going to buckle, okay, is going to buckle, and there is another also type which is like buckling and twisting in the same time, which is going to be studied later on. Okay, now let's go to the maybe last part for our lecture, which is related to example. So let's have let's go to the this example. We have a wide flange 14x74 of A99 99 steel, has a length of 20 feet and pinned ends. Compute the design compressive strength for LRFD and the allowable compressive strength for ASD. Well, in the beginning we are going to check the slenderness ratio. This is the first thing. We need to know which kind of equation that we're going to use. Okay, remember that here we were talking about two types of equation. Here, this part inelastic buckling, this part is elastic buckling. So we want to know FCR will be this equation or this equation. So how we can know this? Yes, using our limit or the F yield over FE, as we're going to see here. So the maximum KL over R is going to be, we're talking about maximum. This means that RY should be minimum. Take care. Stop the video here, go to the manual, check W14x74, what is the minimum radius of gyration for it. Okay, then we're going to find RY definitely, and it is 2.48. Check it, whether it is right or wrong. And then KL, K here we are having 1. Why it is 1? Because we are talking about pinned ends. And then L is going to be 20 feet times the conversion from foot to inches. And we have 96.77, which is less than 200. I'm going to talk about this 200 later, which is the slenderness ratio for us. Okay, And the tension member, if you remember, it was 300, if you remember. We discussed it last time, but here it is 200. Then our limit, 4.71 times E over F yield, is going to be, after substitution here, 29,000. F yield is 50, because we are talking about A99 to steel, then it is 113. So this means that our 96 is much less than 113, right? This means that we're going to use it is inelastic buckling or elastic buckling in this case? Yes, it is something less than this limit. So if we are going to draw, for example, so we have something like this here and then something here. So the limit here. So our point is here, for example, because this is the limit. Our limit is 113. However, this point is, 96. Okay, so we are here. So we are in the inelastic buckling. Then we're going to use our equation that is going to be used is this equation, right? Which is 0.658 to the power F yield over Fe times F yield. This means that we need Fe. We know F yield 50, but we want Fe. So we are going to calculate it in a previous step here. Fe equals to pi squared E over KL over R squared. This means that we know everything. We know E, okay, and we are having KL over R already calculated before here. Then we can obtain the value of Fe and then substitute in this equation, as you can see here, and we get this is the critical buckling strength. This means that 25.21. For this point, the critical buckling is going to be this point, for example, here, and this value is 25.21 KSI. Okay, that's it for this example regarding the nominal strengths. This part is going to be the same for whether that we are designing for LRFD or ASD. There is nothing here. There is no change, because what we have obtained up till now, it is the compressive, critical, compressive or buckling stress, which is going to be used for the nominal strength, which is Pn. It equals to FCR times area gross, as we said, according to AISC. Then area gross, this is from the table, and this one, from the manual, and this one we have obtained it from the previous slide. We are having 449.6 kips. This is the nominal strength. Then we are going to use our LRFD or ASD solution. Okay, so up till here there is no change between, or there is no difference between LRFD and ASD. But after here, after this line, we are going to use LRFD. So the design strength is going to be using the resistance factor time our Pn, nominal strength. It gives us 495. And for ASD, we're going to use exactly 0.6 FCR, which is 0.625. This is based on the allowable stress. So the allowable stress is going to be FA times FA, which is already we have calculated, times the area gross of the section, which is already given from the table, and then this is 330. So the design compressive strength is going to be 495 based on LRFD, and the allowable compressive strength is going to be 330 based on the ASD solution. Okay, so this is how we are going to design our member for LRFD and AS. Okay, so this is for this example. Now let's go to the local stability, and let's discuss about it. So in general, whenever that we have an element, we want to be sure that this element is going to work for us without local stability issues, which is like the flanges, for example, or for the web, that we are not expecting any kind of local instability for the element under the compressive force. We need to safeguard our section and ourselves and our design from the local failures. When I was talking before, I was talking about the global failure. that we have like different element, and then there is a buckling is going to take place here. But the problem is this buckling mode is going to be only for the global behavior. But inside the member it might be that the flange, this protruded part, going to buckle or fail before the large global buckling will take place. So we need to study what we call it local stability. Local stability. The strengths corresponding to any buckling mode cannot be developed if the elements of the cross-section are so thin that local buckling occurs. This type of instability is a localized buckling or wrinkling at an isolated location, as I said, at an isolated location like a flange or a web. Or if we're talking about an angle, for example, one leg of this angle. If it occurs, the cross-section is no longer fully effective. That's the point. Our section that we are designing for is not going to be fully effective, and the member has failed. Okay, that's a very important concept. That why we want to avoid any kind of local buckling, because the cross-section that we are using for the derivation of the equations and for designing and obtaining our nominal strengths is not working anymore. So in this case, we are going to put some limits for this. I and H shaped cross sections with thin flanges or webs are susceptible to this phenomenon, and their use should be avoided whenever possible. Otherwise, the compressive strengths given by ASIC equation 2 and 3, which already we have mentioned, must be reduced. Okay, this is going to be in the case where that we have slender elements. The measure of this kind of phenomena, okay, which is related to the local buckling, is going to be measured with the width-thickness ratio. So this susceptibility is going to be related to the width-thickness ratio of each cross-sectional element. Two types of elements must be considered: unstiffened elements, okay, which are unsupported along one edge parallel to the direction of loading, and the stiffened elements, which are supported along both legs. For example, if we have like white flange, for example, or I section like this. So this web is stiffened from both sides, okay? Because when the loading is applied on this cross section, there is like one element, which is the flange here, and another element, which is another flange here, is supporting the ends of this web. So we are going to call this web as stiffened elements, which are supported along both ends. But if you look to this part of the flange, it is supported perpendicular to the direction of loading, which is already perpendicular to this page. It is supported from this side by the web, but from this side it's not supported. So we call it as unstiffened element, which are unsupported along one edge parallel to the direction of loading. Okay. Sorry, yes, I'm talking about the being parallel to the direction of loading. Okay. Okay. So now, based on this, limiting values of width thickness ratio are given in ASIC like B4, okay, in chapter B, section 4, classification of sections for local buckling. You can stop the video here and go to the specification chapter or part 16 in the manual, and you can find this, where cross-sectional shapes are classified as compact, non-compact, and slender. We're going to talk about this in detail, okay, later on, especially in beams, according to the values of the ratios. For uniformly compressed elements, as in an axially loaded compression member, the strength must be reduced if the shape has any slender elements. That's right. If you have one of the elements that is going to be slender, like the flange, for example, then whatever the type of the strength that we have calculated before, it must be reduced. It must be reduced, okay, as we are going to see. Okay, the width thickness ratio is given the generic name lambda, depending on, this is the width thickness ratio. We're going to talk about what width and what thickness, depending on the particular cross-sectional element lambda. For I or H shapes is either the ratio P over B over T or H over T WIB, both of which are defined presently. Okay, so we're going to define it. For flanges and for WIBs, they are having different lambda. The lambda is going to be different for them. For flanges, lambda is going to be B over T, where B is going to be B flange over T, over 2. So this is the flange here. So we're going to take this part, as I'm going to show in the next slide maybe. So for example here, this is B here for I sections. Okay, so we are going to use B over T, the thickness of the flange. So we're going to use like B over T. It should be less than or equal to a certain limit. We're going to talk about it. Okay, so this is what we call it lambda. For flange, we consider it as what? Unstiffened element. Unstiffened element. Why? Because in the flange, you're going to find that it is supported by the WIB here, but nothing here. So it is unstiffened. But for the WIBs, we are considered to be exactly stiffened element. WIBs are considered to be stiffened element. Why? Because the WIB is like stiffened at one end and the other end in the same time. So this means that stiffened element is going to be, WIB is going to be a stiffened element. Okay, what is the difference between the two? What is the meaning here of unstiffened and stiffened? It will be reflected in the upper limit. Okay, it will be reflected in the upper limit. So lambda of the flange, which is B flange over 2 over T of the flange, the thickness of the flange, which equals at the end B flange over 2 T flange, should not be, or should always be less than or equal to, should be equal, less than or equal to a certain limit. And for the WIB, also lambda, which is H of the WIB over T WIB, should be less than or equal to a certain limit. H of the WIB, it is going to be measured from, it is going to be measured from here, this point here and here. Okay, this is the H of the WIB. It's not the total height of the section. I'm going to give definition for it. The WIBs of I and H shapes are stiffened elements, and the stiffened width is the distance between the roots of the flanges. Okay, there are roots of the flange. So if we are talking about something like this is the flange here, and then at this flange we are having some curvature here. Okay, so we are going to start from here. Okay, that's the point of the roots is here, roots of the flanges. Okay, here. Okay, and the width thickness parameter. So it is the width thickness parameter, which is TW. So we have like limits, upper limits for this ratios, which is lambda. Okay, here you are going to find that the limit for the flange is 0.56. Upper limit is going to be 0.56, the square root of E over F yield. However, for the WIBs, it is 1.49 times E over F yield. Almost the upper limit for WIBs is almost like 3 times the upper limit for flanges. Why? What is this reason? Why this is 1.49 and this is 0.56? Because as we said, this is stiffened. So we are like having some reliability on the cross section because it is stiffened. However, here it is unstiffened. So the section is not going to show this or maybe buckle easily. So here we are putting lower limit for, or lower value for the upper limit. However, here we are putting higher value for the upper limit. Okay, that's the meaning. This is the significance. It is related directly to being stiffened or unstiffened or stiffened. Okay. Okay. You can see the following in the following. You are going to find this in ASIC. Okay. Part B4, you can find it in ASIC B4-B4.1 is given for each case. you're going to find that for all flanges, if we're talking about the wide flange, for example, or let's assume that I section, so we are talking about web and flanges. So the web is B over T should be less than or equal to 0.56, the radical. Here for the web, it is 1.49, the radical, as we said, commonly used like this. And for the T sections, whether that we're talking about the flanges only, it is going to be B over T less than or equal to 0.56. And if we're going to talk about the web, which is here, it is going to be D. Remember, this is D, okay? Seemingly to be D from the above here, this part, D over T, and the value here is 0.75. You need to refer to it from the ASIC before 0.1 section. For angles, for example, B of T for this leg, B over T, is going to be 0.56 times the radical. If they are back to back, seems to be welded here. Here it seems that they are a little bit far from one another. B is going to be measured, as you can see here, and it is going to be 0.45 the radical. For the flanges the same, and for built up sections and HSS or tubes or for pipes. Okay, so we are having in general flanges, we have this limit. For webs we are having this limit, and remember that for webs the limit is higher than the flanges. Remember that well. Okay, now let's have an example and wrap up our video for today. So the example is going to be investigate the column in the previous example 4.2 that we have already done, which is it was I section, and the cross section for local stability. The cross section was W14 by 74, and from you can visit the tables in the manual. You're going to find B flange equal to 10.1 inches, T flange equal to 0.785 inches, and if you are going to calculate B flange over 2T flange, you're going to find it 6.4. However, for our upper limit it is 0.56, the radical of E over F yield. So 29,000 F yield, we are talking about A99 to steel grade, so F yield is 50, SI. This gives us 13.5, which is larger than 6.4, right? This means that there is no local stability issues for the flange. We are talking about the flange here. Now, after that, we're going, so this is here, this is the flange, right? After that, we are going to talk about the web. So here you can see that H over T web equal to D. Okay, take care, because in the web, in the manual, we're going to find this D, the height of the cross section, which is 14.2 for our cross section, which is W14, minus 2K design. 2 times K design. What is K design? So this K design is the design value of K. Different manufacturers will produce this shape with different values of K. So you need to refer to the manufacturer in general. Okay, the design value is the smallest of these values. Okay, the detailing value is the largest. So you are going to have different values of this K. In general, okay, the design value should be always the smallest value if you are going to have different values of K, and the detailing value is the largest. So in our case, you are going to find that this K is 1.38. You can find it, okay, based on the manufacturer, and also you can find it in the manual. So this is the K for us here, and when you calculate it, it's going to be 25.4, which should be less than our limit. The limit for the webs is 1.49, the radical. This gives us 35. We are 25, then we are safe. So this means that the web is not going to have any instability issues, and the flange before it was okay. For us, this means that we are in the safe side, and there is no local stability issues related to the flange or the web for our cross section that we were investigating. Okay, this is the end of this video. Thank you, and see you in the next video.